Hi, I'm Mrs. Edwards, and today we're going to estimate the area underneath a curve using right-handed and left-handed Riemann sums. So our goal is to estimate the area of the blue right there. We're going to start with right-handed Riemann sums. We're going to put in 4 rectangles known as right-handed rectangles and add the area of those 4 rectangles together, and then that's going to be the estimate of that light blue region we just saw. So the way this reads, estimate the area under f of x equals x squared. So there's my curve on the interval 0 to 1. So we want the area from 0 to 1, so the area in there, using 4 right rectangles. There is nothing that says that you have to make your rectangles the same width. Usually in the problem it will say of equal width, or the delta x is, and it'll specify, but I'm going to go with equal widths. I'm letting capital R sub 1 just represent rectangle 1, R sub 2 be my rectangle 2, and so on. All right, so if I'm going to put 4 rectangles between 0 and 1, and I'm going to have a spacing that's the same, I'm going to put a rectangle here where this blue is, one right there where the pink is, and another here, and another here. Okay, those are the locations of my 4 rectangles. Now, when you want to do a right-handed rectangle, then you want to come off of the right-hand side. So notice I have these little dots on the right-hand side, and you want to take that dot and move it up until you hit the function. And that is creating the height of the rectangle. Right, so when that one goes up until we hit the curve, and that one goes up until we hit the curve. Okay, what this has created is the height of the rectangle in that space. Okay, so we're going to add the areas of these 4 rectangles together, and that will be the estimate for the area underneath the curve from 0 to 1. Now, to find the area of those rectangles, first we can say, well, I know that the width is 0.25 in each case. If my interval is from 0 to 1, so 0 to 1, you can always find the length or the distance as big number minus small number. It's very simple in this case, but 0 to 1 would be 1 minus 0, so this distance is 1. And then we're having 4 equal subintervals, so divided by 4. So we get 0.25. So the width of every one of these rectangles is 0.25. To find the area of a rectangle, of course, we want to take width multiplied by height. And so this height happened by substituting 0.25 into the function, and that gives you the y-coordinate. In other words, it gives you that distance. So we're going to substitute 0.25 into x squared, and that will be that distance. The height of the pink rectangle, rectangle 2, if I substitute 0.5 into x squared, that's going to give me the height of this rectangle. And then if I substitute 0.75 into x squared, that's going to give me the height of that one. And if I substitute 1 into the function, f of x equals x squared, that's going to give me that height. Okay, so that's where that notation's coming from. We have the width times the height, the width times the height. All right, so I went ahead and substituted those in. So I got 0.0625 when I substituted 0.25 into x squared. When I substituted 0.5 into x squared, I got 0.25. Substituted 0.75 in here, and I got 0.5625, and I substituted 1, and I got out 1. Now I want to emphasize the point that what I wrote here, these decimals, it's everything. I did not round. You do not want to round until the very end. You never want to round a number that you're going to reuse. All right, so I'm going to now multiply the width times the height the width times the height, the width times the height, the width times the height. And I'm going to have the area of these four rectangles, and then I can add them together. So when I add them together, I get 0.46875. We're not going to make any other calculations, so now I can round. I'm going to go ahead and go out 3 place values because that's what we want to do on the AP exam. So the area underneath this curve is approximately 0.469. Let's take a look at the same problem, but instead of doing right-handed rectangles, we're going to do left-handed rectangles. All right, so same thing. I have R sub 1, R sub 2. Those are just standing for our rectangles. If I'm going to put in 4 rectangles, they're still going to go in this location. But the difference is, since they're left-handed rectangles, between here and here, I want to be on the left side to generate the height. Between here and here, I'm going to be on the left side to generate height. Between here and here, the left side to generate height, and so on. All right, so the first rectangle, I picked this one on purpose because I feel like these kind of weird ones show up on the AP exam where you're like, I didn't make a rectangle. Of course, if this function here comes down to a height of 0, if I substitute 0 into this function, I get out 0, so we never got any height for that rectangle, but that's okay. It's just width times height generated from the left-hand side. So I'm going to move those points up, even though the blue one's not going to go anywhere. Those are the heights of our rectangles. And then I just need to find the area of those 4 rectangles, add them together, and that will be our estimate for the area underneath the curve. So for the first rectangle, second rectangle, third, fourth, all of them have a width of 0.25. So area is width multiplied by height. The function evaluated at 0 gives me the height. I substitute 0 in here, and this is in a minute going to be 0. To find the height of this pink rectangle, I substitute 0.25 into x squared, and that will give me the height of the pink one. I substitute 0.5 into x squared, and that will give me the height of the green rectangle. And then lastly, the red rectangle, if I substitute 0.75 into x squared, that's going to give me the height of the rectangle, the red rectangle. So I went ahead and did that. I just put those numbers in for you. So the width of the blue one is 0.25, the height is 0. And then the width of the pink one is 0.25, and here's our height, width times height, width times height. Then I go ahead and add all of those together. And it's kind of tough to see, sorry, but it's 0.21875. And now that I have completely finished my calculation, I may round at this point, and that's about 0.219. Now notice we kind of had the same process. It was just right-handed versus left-handed, but it's really obvious visually that we have an underestimate here. We can get a better estimate in general by putting in more rectangles. So let's take a look at that idea first. See how if I put all those rectangles in there, there is only a little bit of overhang on these rectangles. So we're trying to estimate the area underneath the curve, and we definitely still have an overestimate, but it is definitely a better estimate than this one. Here we have giant chunks that are overhanging. So if we put in more rectangles over our interval, we will get a better approximation. Eventually, we will learn how to let the number of rectangles in this given space across this interval. We can let the number of rectangles go to infinity, and then we're finding a limit, and that limit would be we're heading towards the area underneath the curve, and we can find the exact area. But for now, we're settling for estimates using right and left Riemann sums. But some observations. If you have a function that is all increasing, notice these first two functions right here, they are all increasing. And then these two functions here, and I'm just highlighting sections. So in the yellow sections, they're all increasing, and in the yellow sections here, they are all decreasing, going downhill. If you put a rectangle to estimate the area under the curve, depending on you using a right or a left, you're going to get an underestimate or an overestimate, and that's going to be true every single time. I don't personally think that you need to memorize that, even though it's a property that is tested on the AP exam. I don't memorize it and regurgitate it. If I want to know, I just make a quick sketch of an increasing function or a decreasing function and draw in a rectangle, and then I can just clearly see without memorizing it. So let's go ahead and do that. Let's just say I am going to put in a random rectangle, that width, between here and here, and I'm going to go with a right-handed rectangle. So going up until I hit the curve on the right-hand side, that's creating the height of the rectangle. So there would be my rectangle, and notice clearly we have all that overhang there. So a right-handed rectangle in an all-increasing piece is going to be an overestimate. So functions that are increasing, right-hand rectangles are overestimates. Okay, here we have an all-increasing function. That's what we're only focusing on the increasing portion. And I put a rectangle between there, and instead of doing a right-handed, I do a left-handed. So I go up until I hit the curve, and that is the height of the rectangle. And clearly that is an underestimate. We have all that extra space in there that has not been accounted for. So if a function is increasing, then, sorry about that, left rectangles are underestimates. Okay, if this next one, I put in a rectangle between here and here, and let's say I decide to go with a right-hand rectangle. So I take that dot and I go up until I hit the curve, draw my rectangle, and clearly we have an underestimate because we've got that extra space in there. So when a function is decreasing, a right-handed rectangle is going to give you an underestimate. Between here and here, let's say I draw in a left-hand rectangle. So on the left side of where I want to draw the rectangle, I go up until I hit the curve and draw in my rectangle. And you can see that overhang there. We have an overestimate. So if you are given that a function is all increasing, or you are given that a function is all decreasing, and you're using either right or left rectangles, you can then declare for sure that you have an over or an underestimate based on these four right here.
Just one other note, if you have a function that has part of it that is increasing and other parts that are decreasing, and you use right-handed or left-handed rectangles, you cannot declare that you have an overestimate or an underestimate, even if it looks like it is an overestimate. Remember, the words "because it looks like it" is not a property. So only if your function's all increasing or decreasing can you declare that you have an overestimate versus an underestimate.
I'm just going to throw in one other vocabulary word at this point, which is monotonic. Occasionally you will hear that word, and monotonic means that it's either all increasing or it is all decreasing. So if you know a section of a function is, say, increasing, but it's a monotonic function, then guaranteed all of it is increasing.